Nevada lies near the center of the Great Basin, one of the driest regions in North America. According to climate data from the National Oceanic and Atmospheric Administration, the average rainfall across the state is only about 180 millimeters per year, and many areas in the south receive even less than that. While the supply of water from the sky is extremely limited, high temperatures and dry air cause potential evaporation to exceed 2,000 millimeters each year. This creates a highly unfavorable water balance system. The amount of water lost from soil, rivers, and lakes is several times greater than the amount of water naturally replenished. According to climate scientists, this prolonged imbalance is what has kept most of Nevada in a semi-desert state for thousands of years. To survive in that environment, the western United States depends almost entirely on the Colorado River basin. This river supplies drinking water for about 40 million residents and supports irrigation for more than 2 million hectares of agricultural land across 7 U.S. states. However, since the beginning of the 21st century, this basin has repeatedly experienced years with low snow accumulation in the Rocky Mountains, the main source of water feeding the river. Climate data analysis combined with tree ring growth records from ancient trees shows that the dry period beginning in the year 2000 is likely the most severe drought in the southwestern part of North America in at least 12 centuries. The most visible consequences appear in the massive regulating reservoirs of the Colorado River system. Over the past more than 2 decades, the total water storage of Lake Mead and Lake Powell has declined sharply because the amount of incoming water is lower than the amount being consumed. In the year 2022, the water level of Lake Mead fell to its lowest point since the lake was formed in the 1930s, leaving it at only about 27 to 28% of its designed capacity. As the shoreline retreated hundreds of meters, objects that had been submerged for decades began to reappear on the cracked, dry ground. The greatest concern lies not in the changing landscape, but in the ability of hydroelectric infrastructure to operate. Hoover Dam, one of the engineering symbols of the 20th century, depends on the water pressure of Lake Mead to generate electricity and regulate river flow. The power plant there has a capacity of about 2,080 megawatts, supplying electricity to millions of households in Nevada, Arizona, and California. If the water level continues to drop close to 895 feet, which is about 273 meters above sea level, the water will no longer be high enough to pass through the downstream outlet system, a situation engineers call dead pool. In that scenario, the water and energy systems of the entire West could face a chain reaction of impacts. Major agricultural regions, such as Imperial Valley in California or Yuma in Arizona, depend directly on water from the Colorado River to maintain production. Imperial Valley alone provides a significant share of winter vegetables and fruits for the United States market. When water supplies decline, the pressure falls not only on agriculture, but also on rapidly growing cities, such as Las Vegas and Phoenix, where populations have risen sharply over the past few decades. For that reason, policy planners have begun to see this crisis as more than a normal drought cycle. Measures such as reducing irrigation or limiting urban water consumption can only delay the problem in the short term. In strategic discussions about water resources in the western United States, an idea once considered too bold has begun to reappear, creating a new water source by bringing seawater from the Pacific coast inland and desalinating it to supply desert cities. From a hypothesis on paper, this concept is gradually becoming a serious research topic as natural water supplies continue to shrink. The heart of the project lies along the California coast, where superscale desalination plants are planned on a scale never seen before. Instead of sending raw seawater deep inland, which would cause severe pipeline corrosion and the risk of irreversible soil salinization, the entire treatment process is carried out directly at the source. The core technology is reverse osmosis, using extremely high pressure of about 1,000 psi to force seawater through a semi-permeable polymer membrane. where only water molecules are allowed to pass, while salt, bacteria, heavy metals, and microorganisms are retained. Thanks to a new generation of membranes combining graphene and pressure recovery systems, each cubic meter of fresh water today requires only about 3 to 4.5 kilowatt hours of electricity, nearly half the energy required 2 decades ago. Although reverse osmosis has already been commercialized in places such as the Carlsbad plant in San Diego, the Nevada project is dozens of times larger in scale, bringing the risk of membrane clogging from marine algae and organic matter, forcing operators to run complex pretreatment chains, from sand filtration and nanofiltration to continuous biological removal. Maintenance costs for the membrane system alone can account for as much as 35 to 40% of the total annual operating cost, equivalent to hundreds of millions of US dollars each year at the scale of this mega project. The breakthrough in the design lies in the pipeline route. Instead of cutting across nature reserves or clearing densely populated residential areas, the system is proposed to be buried underground along the corridor of Highway 95 and abandoned railway lines, taking advantage of existing infrastructure rights of way to reduce legal conflicts and ecological impacts. Along this route, booster pump stations will be installed at intervals of 80 to 120 kilometers, accompanied by an ultra-high voltage power transmission network. The main pipeline is expected to have a diameter of 6 to 8 meters, nearly the size of a subway tunnel, capable of transporting more than 200 cubic meters of water per second, with pressure on uphill segments exceeding 150 bar, requiring the use of reinforced carbon steel alloys combined with composite materials similar to those used in transcontinental gas pipelines. The pumping corridor would cross the Mojave Desert, following ancient fossil riverbeds with gentle slopes to move deeper into the Nevada Plateau. The greatest challenge, and also the center of opposition, is gravity. Nevada sits on the Great Basin Plateau, where the target valleys lie at average elevations from 1,000 to 1,700 meters, while the Sierra Nevada range and coastal mountains form massive topographic walls separating the ocean from the interior. According to the laws of thermodynamics, the energy required to lift enormous volumes of water to such elevations cannot be avoided. To pump 1 million cubic meters of water up about 1,200 meters already requires power at the level of several thousand megawatts. And to maintain enough flow to form artificial inland lakes, the system would have to operate at 6 to 8 gigawatts of electricity continuously, equivalent to the output of 6 to 8 large nuclear reactors, or the entire electricity demand of a megacity with several million residents. Compared with this number, the maximum capacity of about 2 gigawatts from Hoover Dam is like a spoonful of water in the ocean, meaning at least 3 to 4 Hoover Dam scale facilities would be needed just to operate the pumping system. If the electricity came from fossil fuels, the project would emit more than 20 million tons of carbon dioxide each year, equal to the emissions of a small country, turning a drought mitigation plan into a new climate disaster. At this deadlock, engineers propose turning the desert into a massive energy plant, deploying a solar power belt covering hundreds of square kilometers, combined with plateau wind energy to generate 10 to 12 gigawatts of renewable capacity, while using the artificial reservoirs themselves as pumped storage hydropower systems to store electricity at night. In other words, water generates electricity, and electricity lifts the water upward again. A closed energy cycle never before attempted on a continental scale. California and Nevada are two of the leading states in the United States for renewable energy, especially solar power. California currently has more than 42 gigawatts of solar power capacity, while Nevada is aiming for a target of 50% renewable energy by the year 2030. However, the rapid growth of solar power has created the famous duck curve. During the day, when sunlight is strongest, the amount of electricity produced becomes so excessive that the grid cannot absorb it all, forcing operators to curtail production or sell power at negative prices. In contrast, when the sun sets in the evening, household demand rises sharply while solar supply disappears completely, forcing the use of expensive and polluting natural gas power plants to compensate. The lack of large-scale energy storage systems is a critical weakness of the Western power grid. The Pacific Water Transfer Project is designed to solve exactly this problem through pumped storage hydropower technology. Instead of being only a one-way water pipeline, the system would operate like a giant battery. The operating mechanism works as follows. Pumping phase, or charging the battery. During the day, when solar electricity is abundant and cheap, the system uses this energy to run large-capacity pumps, pushing water from sea level up to intermediate reservoirs on high mountains, or directly into reservoirs in Nevada. At this stage, electrical energy is converted into the gravitational potential energy of water. Discharge phase, or releasing the battery. At night or during peak demand hours, when the grid experiences shortages, water from higher elevations is released downward through pressure pipelines, spinning turbines that generate electricity and send it back to the grid. With a round-trip efficiency of about 70 to 80%, this technology is far more effective than manufacturing large-scale lithium-ion batteries to store electricity. The project turns Nevada into an energy warehouse for all of California, helping stabilize the power grid across the southwestern region. The enormous energy cost required to pump the water is therefore offset by the difference between peak and off-peak electricity prices, while also solving the problem of excess renewable energy. Even if the energy problem has a solution, the initial investment of $16 billion remains a financial barrier that is difficult to overcome if revenue relies only on selling fresh water. The golden key that makes the project financially viable lies in the byproduct of the desalination process concentrated brine. In the reverse osmosis process, every 2 liters of seawater input produces 1 liter of fresh water and 1 liter of concentrated brine. Traditionally, brine has been considered hazardous waste. Discharging brine directly into the ocean can increase local salinity, kill bottom-dwelling organisms, and damage marine ecosystems. But in the modern economic context, brine is actually liquid ore. When seawater is concentrated, the concentration of valuable minerals doubles. The world is shifting toward the era of electric vehicles, and green energy and lithium, the lightest metal, is often described as the new oil or white gold. Lithium is an irreplaceable component in lithium-ion batteries. However, the global lithium supply chain is currently dominated by China and South America. For the United States, securing a domestic lithium supply has become an issue of national security. Seawater contains lithium, magnesium, rubidium, boron, and uranium. Although the concentration of lithium in seawater is lower than in salt deposits in Chile or Argentina, the enormous volume of water processed every day in this project means that the total output could be very large. The Nevada project proposes integrating direct lithium extraction technology directly downstream of the desalination plants. Direct lithium extraction uses selective adsorption materials to capture lithium ions from brine without waiting months for evaporation, as in traditional methods. This economic model is already being demonstrated in the Salton Sea region of California, an area often called the New Lithium Valley of the United States. Major corporations such as Berkshire Hathaway Energy, General Motors, and Energy Source Minerals are investing billions of US dollars to extract lithium from geothermal brine with estimated reserves of about 600,000 tons per year. If this model is applied, the Nevada project would no longer be a water infrastructure project that consumes money, but instead a highly profitable mining and energy complex where fresh water becomes a low-cost byproduct used for environmental restoration. Although the economic and energy calculations appear attractive, Many ecologists still warn that creating massive artificial lakes in the middle of the desert could bring consequences that are difficult to reverse. A commonly cited example is the Salton Sea in California. The Salton Sea was formed in the year 1905 when an engineering accident caused water from the Colorado River to flow into the Salton Sink Basin for nearly 2 years. At first, the area became a famous tourist destination, but because the lake has no outlet to the ocean, water can only leave through evaporation. Over more than a century, continuous evaporation has caused salt and dissolved substances to accumulate. The salinity of the lake is now about 70 to 75 parts per thousand, nearly twice the salinity of seawater. This has led to repeated mass fish die-offs, harmful algal blooms, and severe declines in the aquatic ecosystem. As the lake level drops, the exposed lakebed reveals agricultural sediments that have accumulated for decades, including arsenic, selenium, and pesticide residues. Desert winds can lift this fine dust into the air. Some studies suggest that the Imperial County area surrounding the lake has higher childhood asthma rates than the average level in California. Opponents worry that new artificial lakes in the Nevada desert could repeat a similar cycle. With evaporation rates of about 2 to 3 meters of water each year, if the system lacks mechanisms to remove salt or maintain a stable water supply, these lakes could gradually become more saline and lose the ability to sustain ecosystems. Beyond the issue of salt, creating large bodies of water could also change the surrounding desert environment. Increased humidity may allow invasive plants such as cheatgrass to spread. This grass dries quickly in the summer and ignites easily, increasing the risk of wildfires in ecosystems that historically experience very few fires. Some scientists are also concerned about extremely rare species in the region, such as the devil's hole pupfish, a species that lives only in a single water-filled cavern in Nevada. Even small changes in groundwater levels or water chemistry could affect their fragile habitat. For this reason, the debate surrounding inland sea projects is not only about engineering or economics. For many scientists, the more important question is whether humans can fully control the new ecosystems created in the middle of the desert, or whether we are repeating mistakes that have already occurred in the past. If the project becomes reality, it would mark a major transition. Humans would no longer simply adapt to arid environments, but would begin using engineering to redesign the water and energy systems of an entire desert region. In the best-case scenario, Nevada could become a new model for arid regions around the world, where technology helps create water supplies, energy systems, and even artificial ecological spaces in the middle of the desert. But whether successful or unsuccessful, projects like this reveal a defining reality of the 21st century. Humans are increasingly becoming environmental engineers of their own planet, where science and infrastructure are being used to reshape ecosystems once considered permanent.